I'm going to go ahead and share my screen and we will jump right in. We've got a lot to cover today. All right. Welcome everyone to build enterprise grade Q&A at scale with Open LLMs on AWS. We are absolutely thrilled to have you here today. My name is Amanda Wagner. I'm the Senior Community Manager at Pinecone. And if you are not familiar with Pinecone, Pinecone is a vector database that makes it easy to build high-performance vector search applications. Of course, more on that a bit later. Now, before we jump into today's workshop, we do have just a few housekeeping rules. Number one, we ask that you use the chat for chat. Go ahead, say hi, let us know where you're coming from, let us know what you're building with Pinecone. But when you have a question, which we hope you will, we ask that you add those questions to the Q&A portion of the Zoom and not the chat. Again, questions in Q&A, chat in chat. This helps us stay organized. We tend to reserve around 10 to 15 minutes at every workshop for your questions, and it helps us get to as many questions as possible. If you miss something, no worries. This event is being recorded. We will share this recording with you after the event, as well as share on our YouTube and our social media channels. So if you are not subscribed and following, I highly recommend you do so today. In that email, there's also a post-event survey. Take 5 seconds, fill that out. It helps us bring you more, bigger, and better content in the future. If you have questions after the event, we ask that you ask them in our community forums, which you can access via Pinecone's website. Now, without further ado, I'm going to hand it over to Vedant to introduce himself and tell us a little bit about the workshop.
Great. Thanks so much, Amanda. And let me just share my screen real quick. Yeah, and hello, everyone. Thanks for joining. My name is Vedant Jain, and I'm a Senior AI/ML Specialist here at Amazon Web Services. Today, we will discuss how to build enterprise-grade Q&A at scale with Open LLMs on AWS. And we have a packed agenda today with exciting features showcasing generative AI capabilities on AWS for your enterprise, which I will talk about initially. After that, we will deep dive into Retrieval Augmented Generation, or RAG for short, with Roy and Pinecone, followed by Fee describing the role of Anyscale platform in addressing scaling challenges encountered in the RAG architecture. Stick around till the end because we'll end with a demo of we'll end with a demo of Pinecone and Anyscale working together to build a scalable Q&A application, as shown in the diagram. Outside of just scaling the query engine, there's also challenges of scaling the generation of vector embeddings itself. But before we get into that, let's talk about the generative AI for the enterprise. There's a boom in the adoption of Gen AI across the enterprise landscape in early vertical markets. Companies are taking openly available and proprietary foundation models and adapting them to a wide range of use cases. Generative AI is being used for drug discovery, generating protein embeddings, and even in media and entertainment for generating highly personalized content, just to name a few. And in just last week's announcement, Amazon will be offering its users with an AI-generated summary of product reviews to offer a better and more reliable purchase experience. Also, we at AWS regularly work with both small and large enterprises on their journey towards successful adoption of generative AI. And we are continuously uncovering challenges and working backwards in solving them. So let's discuss some of those challenges. Firstly, if you're an AWS customer, your enterprise's compliance and regulatory guidelines often preclude you from moving your data outside of AWS, only for building applications, or even worse, send to a generative AI model or application provider who can store and use your data for their internal use. At the core of a Q&A application is a foundation model, or often referred to as a large language model. And these models are created using large swaths of data. And I can assure you that almost excuse me, just yeah, and I can assure you that almost all of our enterprise customers have their data spread across various AWS data services such as S3, RDS, DynamoDB, and other partners and ISVs on AWS. When building GenAI applications for domain-specific use cases, fine-tuning or augmenting a foundation model, you need to take the model to the data rather than bringing the data to the model, which can get costly very quickly. Then there's a question of scaling compute reliably and efficiently. There are various stages in a RAG-based approach, and oftentimes being able to scale the underlying compute framework to meet the enterprise knowledge base demands becomes a bottleneck in delivering these applications to end users successfully. And finally, you need to ensure that the data delivered to the end user by the application is fast and delivers up-to-date and accurate information. For example, a Q&A application which has domain expertise in COVID-19 needs to be kept up to date as new variants are detected and new vaccines are released. Otherwise, the system will become stale very fast. So how does AWS mitigate these challenges? Well, in a number of ways. Firstly, we work backwards from our customers. Specifically, when building GenAI applications, we see that users have to pull data from a wide variety of sources, depending on the modality type. Whether you're working with text data, images, audio, video, etc., you will run into having to get the domain data from these different data sources, such as S3, RDS, and others. Next, there are different parts of the GenAI architecture which will require different instance types, with certain instances optimized for training and others optimized for serving, for example. And then there is the question of the underlying compute framework itself. Depending on the sophistication required, you may choose to use a serverless service, or if you need more control and customization options, such as being able to use spot instances or manually choosing the number of instances for cost control, AWS provides many options to users to customize the architecture for their need. Which brings us to our next point. Customizing your architecture on the foundations of machine learning Lens, which is the well-architected framework for machine learning, allows users to follow a time-tested and operational architecture best practice for designing and operating these machine learning workloads in the cloud. For example, enterprise security guidelines often stipulate that enterprise data does not leave AWS. Since all the data being used to fine-tune and augment the foundation model, as well as the responses generated from the application, are encrypted and stay inside of AWS, you can trust that your data will remain private and confidential. Once you have a customized architecture for your business, AWS allows you to leverage the most cost-effective infrastructure for generative AI. You can deploy on the right instance type for the use case with the availability of both training optimized as well as inferencing optimized instance types. From A100s to custom-built silicon, such as AWS Trainium and Inferentia, enterprises benefit from the best price-to-performance ratio for their generative AI workloads. Then there's the combination of AWS Marketplace, SageMaker Jumpstart, and Amazon Bedrock, which provides you with a large selection of large language models, both that are publicly available as well as proprietary, such as the ones built by Cohere, AI21 Labs, Stability, just to name a few. And finally, our network of partners, as well as first-party services, allow users to pick from best-of-breed products, as well as use solutions available in the open source, such as AWS Samples, which you can quickly download, customize, and run for your enterprise. One of the most common solutions used for addressing generative AI challenges is retrieval augmented generation. And I'm going to pass it over to Roy from Pinecone to discuss further. Thanks.
Thanks, Vedant. Just going to share my screen. Okay. Can you see my screen? Vedant, can you just give me a high thumbs up?
Yeah, you're good.
Okay, cool. Thank you. Hi, everybody. So my name is Roy Schwaber-Cohen, and I'm a staff developer advocate at Pinecone. And today I'm going to talk to you about retrieval augmented generation with Pinecone. And then later on, Fee is going to demonstrate that work with Ray and Anyscale. So I'm going to talk about 4 topics today. So we're going to very briefly cover the topic of what vectors and embeddings are. And then we're going to talk about what a vector database is. We'll review an application architecture for any kind of application that uses a vector database, and then we'll see how that can apply specifically to retrieval augmentation generation. So first, let's talk about embeddings. So embeddings are the foundation of basically everything that we're doing when we're talking about RAG. Essentially, they are numerical representations, long list of numbers, essentially vectors, that carry within them the meaning, right, of that comes out of relationships between different objects. And those objects could be words, they could be documents, they could be potentially images. And basically what happens when we create an embedding is that we're essentially taking that information, that meaning information, and we're projecting it from the space that it lived in. For example, it could be like word space or pixel space, and we're projecting it into vector space, and hence the word embedding. We're basically embedding that information from one space to another. To basically get a better intuitive understanding of how embeddings work, we can look at this visualization that very simplifies a lot, like how these embeddings live within this high dimensional vector space. Here, of course, we have only 3 dimensions, but this will basically help us understand the underlying behavior. So when we have a set of terms, surface forms, that have some semantic correlation, what we'd expect to have is some geometrical proximity or closeness of these embeddings within within this within this high dimensional embedding space, and they're going to be close together. And terms that have less to do with that have less similarity with one another will be farther apart. So, for example, in this slide, we can see 3 sentences that basically look at the word bank, right? And what we see here is that the meaning of the word bank is influenced by its context. So it's not only that we have surface forms and the meaning of the surface forms in and of themselves, but rather, as we expect from language, the meaning comes from the context of the word in which it is found. So here we have, where's the Bank of England, and where's the grassy bank, and how does a plain bank? In each one of them, the meaning of the word bank is different, and so the embedding of the entire sentence and the word bank inside of it is going to be slightly different. And so, conversely, if we look at an example where we have 2 sentences that use very different surface forms, but have very similar meanings, we'll expect to see them very close together within high-dimensional vector space. So, what is a vector database? How does it factor into all of this? So a vector database, as the name suggests, allows us to manage vectors like these embeddings at scale. So basically, it allows us to quickly write them and update them and delete them as necessary. And of course, most importantly, it allows us to read those vectors and query vectors based on some similarity metric. So in order to query a vector database, we have to take our query, create an embedding out of that query. We have to take content, embed that content, upsert that content into our vector database, and then use that query vector to retrieve other vectors that are similar to the query vector that we have. And then also, very importantly, a vector database also allows us to associate some structured metadata with each one of our vectors. So it's not that like these vectors are just live there in the database with no other data other than some foreign key, but we can actually use some additional metadata that can help us downstream to do all sorts of things. For example, we could do optimization. So instead of searching through the entire vector space, we can search on subsets of that vector space by leveraging the metadata. And as we'll see in the RAG example, we can use the data to improve our results and actually refer to, again, structured data and trusted data that will be beneficial for the application overall. Pinecone, if you don't know already, is a high-performance vector database. It was built to be a distributed vector store that can scale infinitely. Allows you to create and manage and scale your indices using an API or the console. The whole premise behind Pinecone is it's very easy to use, but it's also capable of handling hundreds of millions and even billions of vectors while maintaining low latency and high performance, and of course, a manageable cost that kind of makes sense and doesn't go out of hand. Okay, so let's take a look at an application architecture for an example application that we see very commonly with Pinecone, and that is semantic search. And in fact, semantic search is the basis for RAG applications as well. So as you can see here, there are essentially two tracks. The first track is basically us taking the content, using an embedding model to extract the vector embeddings from that content. Alongside, in parallel to that, we take the metadata that's associated with the content that we want to associate with those vector embeddings that we've generated, and then we use the API to upsert those vector embeddings and their corresponding metadata in the vector database. And then the second track is we have the application itself, and when it wants to use those vector embeddings, it will take the query the user has provided, and then it's going to use the same embedding model to create embeddings for that query, and then retrieve similar vectors and their associated metadata based on that query vector, like I mentioned before. Okay, so now let's talk about retrievable augmented generation. So as Vedant mentioned, generative AI is indeed quite powerful and explosive, and we see it basically everywhere. There's so many different use cases that are incredibly powerful and compelling. But of course, generative AI, as we all know, has a lot of limitations put on it. The biggest one of which is the fact that generative AI models and other models, right, are limited by their initial training data set, right? It's very hard to basically retrain a foundation model, and even doing fine tuning is not a trivial task. And so what we usually end up with is being limited by the initial training data that model was created with in the first place. And so the way that this problem manifests in our applications is that the models respond with answers that might have incorrect information in them. Essentially, it could be even invented information, and it became to be known colloquially as a hallucination. So how does a vector database like Pinecone, how does it help with fixing this problem of hallucination? So vector databases can help mitigate these hallucinations, not fully solve them in and of themselves, but mitigate them to a very large degree by providing some anchor to this set of what I call real-world semantic and trusted structured data. So again, you can think of other types of data sources like a SQL database or like a graph database, et cetera, that you could potentially use to mitigate hallucinations. But specifically with RAG, the input for these systems is usually semantic, right? So someone is going to use natural language to express their intent. And so because of that, we are very likely to run into ambiguity, and it's going to take more of a semantic approach to kind of realize the user's intent and actually provide information that actually is relevant to that user query. And so what happens with RAG solutions is that we basically build the same way that we build a knowledge base for a semantic search engine. We build an embedded knowledge base in the vector database, and then when the query comes, we use the user's prompt to retrieve semantically relevant content, which is incredibly easy to do with a vector database. And then we take that semantically relevant content and we inject that into the context window of the generative AI model, and that will be the response from that point on. And of course, it's important to mention that, again, we have not only the content of the initial knowledge base that has been embedded, but we also have all of the metadata that has been associated with that knowledge. So for example, we can have links and other types of references associated with the content that we are using to generate the user response. And so we can give things like citations and so on and so forth, show images as part of our response, and we're not limited to only use the content itself as part of the response to the LLM. So the RAG architecture is very, very similar to the one that I showed for semantic search, as I said before. So nothing here really changes, except for, again, that when the response comes back from the vector database, we take that response and we do what's called context stuffing or prompt stuffing, and we send that information back to the LLM, and then we use prompt engineering to basically require the LLM to refer only to that context that we provided when it's producing an answer to the user's query. So here's some best practices that we found out over the span of several months that we've been experimenting with RAG here at Pinecone, and from what we've heard from different users. So the first of which is you're not limited to using the same model for creating your embeddings for retrieval, and then for your text generation. Those could be completely different models. And in fact, you might find that using a smaller, lighter, and faster model for creating the embeddings actually might work better, both in terms of cost and performance. Then there's the issue of chunking, which is definitely one of the most asked about questions when it comes to RAG. And there are several things that you might want to consider when you think about going about chunking your data. First of all is, of course, what are you indexing, right? Are you indexing short bits of text, or are you indexing long form text like contracts or documents like guides, et cetera, et cetera. You want to consider what embedding model you're going to use, and of course, if your content matter is short and on a sentence level, you might consider using a sentence transformer. And of course, you then want to chunk your text accordingly. And if your content matter is long, you might use a different model that is better tuned to deal with that type of content. You want to think about the relation between the query and the retrieved data. So there are many variables in the way that the user might choose to query your system. They might have long form questions. They might have very short form questions. And the retrieved data against it might work differently depending on the length of the text itself. So we want to consider that as well. There are, of course, technical considerations about the actual form factor of your content. So, for example, if you have HTML or Markdown content, you can use what's called content-aware chunking. So Markdown chunkers, and for example, like there's like tech chunker that will actually look at the content and use the semantic information within that content to break it up. Versus approaches that are more programmatic, in which you might not have that luxury, and you'd have to fall back on recursive kind of a recursive chunking or other kind of fixed length chunking instead. The last three topics that I'd like to mention, first is query expansion. So queries again can be very opaque. Users might not actually have like all the information that they want to know about when they're asking their questions. And so you might have to do some work to actually improve upon the actual query so that the results from the retrieval are actually beneficial. You definitely want to leverage your metadata. Like I mentioned before, metadata could be very rich. It could plug into other system, could reference other system that you may have. And the journey doesn't have to end with just the text that's going to be part of the context sent back to the LLM. And of course, the last thing is there are numerous ways to monitor and evaluate your the performance of your RAG system. A couple of examples for monitoring, I'd like to mention Langsmith, that was made by the creators of LangChain. That is an incredible tool for actually getting a better understanding of how exactly your models and chains are being used together, and how your store is performing, et cetera. And one evaluation technique that I've heard about recently that I find incredibly helpful is you can actually create very simple quizzes that specifically for RAG system. You can create quizzes that basically the answer for ahead of time, and you can basically see whether or not your system can correctly answer these quizzes, and if its performance is improving over time or remains the same. And with that, I'm going to hand it to Fee. Thanks for listening.
Thank you, Roy. Very insightful about all those tidbits and best practices around chunking and just RAG in general. Okay, let me share my screen. Okay, so my name is Phi Nguyen. I am a technical product manager on the Anyscale team. And before I jump into the demonstration, I just would like to give a quick overview and introduction to Ray and Anyscale for those who are new to Ray and Anyscale. So Ray is an open source framework to help developers and ML practitioners to scale the existing machine learning and Python workload. It is being used in production by many organizations of all sizes today to help them with their machine learning practice. These are a few numbers to give a bit of an overview of different areas where Ray has provided some benefits to users. So 23 times a better throughput is how we have optimized using Ray to do LLM serving. So we've used VLLM and continuous batching, and we have a blog post about it, and how we were able to improve the throughput by 23 times compared to just a standard techniques of serving LLM. 75% lower cost is the number that a customer called Sewer.ai has experienced using Ray and Anyscale. Previously, they were using AWS Batch and some solutions on Kubernetes, and by migrating and adopting Ray, they were able to experience a 75 better price performance. 60 seconds is the time it takes to launch a cluster of 1,000 nodes. And so it's super quick to launch a cluster on the public cloud, such as AWS, run your workload and spin everything down and really take advantage of the elasticity and the compute available on the cloud. $1 per terabyte is the new record that the Ray team has established. And this record is all about shuffling 100 terabyte. It used to belong to Spark, and now we've shown that by using Ray, you can shuffle at a better price performance, so about $1 per terabyte. So these are just a few insights about where Ray has been impactful in the realm of machine learning and data processing for machine learning specifically. So Ray has also been used by OpenAI to train ChatGPT. I talked about the benchmark before. Other cloud providers such as Google Cloud and AWS are also embedding Ray in their own service and offering. And we have industry-leading practitioners such as Spotify, Instacart, and Netflix using Ray. So for example, Spotify is using Ray to really evolve the existing Kubeflow implementation. Kubeflow turns out not to be as flexible for those newer use cases. And so they found Ray to be flexible enough and also allow them to scale. Similar use cases for Instacart and Netflix. And these are all public blog posts that you can find them online and read through them. So more specifically to Gen AI, OpenAI, Greg Brockman came to our summit last year, part of a fireside chat, and he discussed how they went through evaluating Spark and Dask for helping them to scale training the largest language model, for example, and they've landed on Ray to help them. They found Ray to provide just the right level of abstractions, a low level, but also solve some of the complex problem, with dependencies, scheduling, and orchestrating those complex workload across a large cluster. Uber is known to be the pioneer in at least writing about building a machine learning platform, and they are now migrating Uber Michelangelo that was based on Spark and many different pieces of software that were stitched together onto Ray. And so now with Ray, you can use one platform to scale all aspects of your machine learning practice by using a single Python script, right? So, and then finally, Cohere. Cohere is also a big LLM provider, and they also came in the summit last year and talked about how they're using Ray to scale workload across thousands of GPUs. Okay, so Ray has many different API and library. At the lowest level, we have what we call the Ray core API. So very easy to use. You can just decorate your existing Python function or Python classes, and then scale your workload across a Ray cluster. And Ray will just know how to schedule which function on which machine, and really help you to seamlessly scale your Python workload. Above that, we have what we call the Ray AI runtime, or Ray Air. And it is composed of many different library, higher level abstractions to really help you to scale each step of the machine learning workflow, right? So data loading, training and tuning, reinforcement learning as well, but also model serving. And so in the demo, we'll see how we can use the Ray data library to scale the embedding process. Okay, and then Anyscale is the company behind Ray, the open source framework. We also offer a commercial service and product. And so, we allow you to add additional features on top of, your Ray workload. So we have optimized the compute. And so by using Anyscale, a managed platform, you can spawn thousands of Ray cluster, and it takes, less than 60 seconds to spawn each cluster. You can seamlessly build your workload that run across CPU, GPU, Graviton, Inferentia, Trainium, and TPU. We have multi-cloud capability, and so you can easily orchestrate one workload to run on a given cloud, given region, and then another workload to run on another cloud, another region, right? So we make it cloud agnostic. And we also have a smart instance selection, giving you a good trade-off between availability to run those workloads and not having any disruptions, but as well a better price performance by leveraging Spot whenever it is needed. So, giving you the configuration to really allow you to sort of balance those trade-offs. In terms of developer productivity, we have a managed workspace, Anyscale workspaces, a managed IDE to allow you to use VS Code, a Jupyter Notebook on top of a Ray cluster that is elastic. And so really allow you to have that interactive, scalable experience to really help you accelerate prototyping some of your workload that require scaling. We also have an API feature. So, going from an experiment to operation, you can easily transition onto a batch job that you need to schedule on a regular basis, or a real-time endpoint. And then obviously observability and debugging capability, as well as monitoring and alerting, are just like part of the stack for a developer to help them, allow them to troubleshoot the application. And then finally, in terms of security and governance, the typical sort of guardrails that we provide to allow you to build within your AWS account properly. We have SOC 2 Type 2 compliance. We also architected the product to be built for the cloud, so you can bring your own AWS account. We deploy all the Ray cluster in your account, and so the data plane is in your account and isolated from the external world, and including ourselves, our service. Okay, so Anyscale powered the Gen AI stack, and so this is my interpretation of the Gen AI stack. So we have on the top level, building your applications, and you may be using different web framework, or you need to incorporate with existing applications. And then we have in-context learning and fine-tuning framework. And so one thing that we are finding with LLM is that most developer can treat an LLM as a black box, text in and text out. And they have now a very powerful capability to build those intelligent applications without having to understand math or being a data science expert, right? And so that's really opened up the access and democratization of building those LLM applications for a developer and not needing an ML practitioner. And then, obviously, if you need to customize and extend your model, some provider are providing fine-tuning as a service. And so you don't ever need to understand math. You can just pass a few examples from data and then, get a custom model. But, you can also pre-train or fine-tune your foundational model or your LLM. And it is very exciting now with Llama 2 on top of different compute. So on the top, the application, we have what we call Aviary. Aviary is an open source LLM application to help you evaluate multiple LLM models. So I have an example here. I'm just going to quickly show you how it works. So this is a public URL. You can have access and try it. This has also a GitHub repo if you're interested in deploying this application on your laptop or on your server. You can also do so. So I'm just gonna pose a question. And then one of the interesting things is that I've picked 3 different models, and we have many different open source models that you can pick. We also have the Llama 270B. And so what is interesting here is that I'm showing the different latency, also the different token, and these are all indicator of good characteristics of, is this open model suitable for me in my use cases in my application to be deployed in production. I can also vote for the best answer that I think it is. And then, imagine that you are crowdsourcing within your organization and get more signals about, which model is performing better. You can also use that data set as a, virtual cycle to then allow you to fine tune on, the best answer that people have voted to, should you need to improve the model. Okay, again, so this is open source. Feel free to check it out at a later time. And then one layer down, we have in context learning and fine-tuning framework. We have a different service called Anyscale endpoint. So think of it as OpenAI for Open LLM. So it's completely serverless. You pay by the number of token. The pricing is $1 per million token, which is about 45% lower than ChatGPT. And currently we are serving the Llama 2 models. The Llama 270B is are showing, based on literature, similar performance to a ChatGPT. So very exciting for the one that users are preferring open source or Open LLM. So very easy. Again, in the demo, I'll show how you can use Anyscale endpoint to really build this RAG application in conjunction with Pinecone. And then if you need more customization or more data privacy, you have some concern about governance and data privacy, you can always use the Anyscale platform. I mentioned before, it was built in architecture for the cloud. And here you have all the bells and whistles and low-level framework to really help you fine-tune, pick different framework that you want to use to further extend your LLM practice. And then finally, we have the very open source. I mentioned the framework. And so if you need like maximum control about the whole stack, or if you prefer, Kubernetes and running your own infra, you can choose to use KubeRay, the plugin for running Ray, and serve those LLM model, or do fine tuning or pre-training for your LLM. Okay, so the demo for today, what we're going to be doing, we're going to be using Llama Index as a data or sort of an ETL abstraction. We're going to be using Pinecone as a vector database, and we're going to be using Ray to scale the embedding process. And we're going to be using Anyscale endpoint to then generate the responses based on the Llama 270B model. The one thing I would like to highlight is that, Boy has gone through all the different best practices about chunking and different embedding model. And so, we may recognize that you may need to load a number of set of data. You need to have some different kind of chunking strategy based on the use cases in the application that you want to build. And so being able to generate those indices very quickly using Ray is really going to accelerate your prototyping time so that you can really land and better fine tune or better develop those applications around RAG and LLM. Yeah, so this is taking a request. We're going to take the query. We're going to embed the query. We're going to retrieve the most relevant chunk of data based on the Ray documentation and the Ray blogs. And we're going to return the top 3 most relevant chunk. We're going to build a prompt based on that context, and we're going to pass that prompt onto Anyscale endpoint. And we're going to sort of mitigate the hallucination and get an answer from those LLM model. Okay, so let's jump into the demo. So I'll share the link to the the Git repository, but I'm using Anyscale. But you can, if you have a GPU, you can use example. This is only using one GPU. But if you just want to use CPU, you can also run the embedding process on CPU. And then using Ray is just as simple as pip install Ray. Just for the sake of our demo today, I'm just using one EC2 instance or on top of Anyscale using one GPU. So I'm going to kick this off, and then I'm going to walk through the code here. So I'm going to press play. So you can see here at the bottom, I kicked it off, and it's going to run, and it's going to ingest all the documentation and the blog, right? So let me walk you through what the code does succinctly. So we're using the Llama index abstraction for the Pinecone vector store. And so this is how we initialize and define a vector store, in this case, Pinecone. There's a couple of functions that we need to perform before we can ingest that data and create the embeddings onto Pinecone. So first we need to load and parse the file. So in this case, we only want the HTML file and sort of filter through the the images and the JPEG. We also convert those documents into nodes, and node is a Llama index abstractions. And so we want to make sure we follow those different abstractions. We are using an open source embedding model. In this case, we're using sentence transformer or MPNet base v2. And you can see that this is upon starting a class. And the reason we're using a class is because we want this process to be stateful and stay in memory, so that for each batch, we don't need to reload the model into memory. We can just load the model into memory once, and then each batch can just call that stateful or class to run through the inference or through the embedding process. Okay, so this is the code to actually perform the embedding process. And so now is the time to take Ray data set and pull everything together, right? So here we are reading all the data from all docs, and this is the path to all our files. We are loading and parsing the files, just like I mentioned before. Sorry, I want to pause this and just want to highlight that we are actually processing and uploading those documents into Pinecone right as we speak. And so you can see this cursor at the bottom. So going back into our data set, so we load all the files, we converted them into node, and this is the process of embedding each of those documents. So you can see here that we are specifying the batch size and the number of GPUs. So if you had 4 GPUs, you can just mention 4 GPUs. If you have 2 machines of 1 GPU each, you can mention 2, and then Ray will automatically schedule those different actors or different classes to be run on different hardware, right? Without having you to really sort of schedule automatically or manually on a given machine. And then, finally, just gathering everything together and then converting into a different object. This is just a Llama index abstraction quirk. And then we're just adding all the documents into Pinecone. And that's essentially what you saw. And then we repeat the process for all the blocks. And that's really all it is. And so if I switch over to my Pinecone console, you can see that I have some activities, and I have about 80,000 vectors in my Pinecone. And this is the startup or the starter account offering. And so, you can run through this application and this example for free. Okay, so that was the first part of our demo where we, ingest at scale. So imagine that, we have different chunking or embedding strategy. What we need to do is to tweak this and create maybe a different index, and then, just rerun this code, right? And as you can see, it took, less than a few minutes to embed all the documentation and the blogs from the Ray website. Okay, so let's switch over to our query. So this is the second part of the demo. And so, in this case, I'm using the Anyscale endpoint API key. So if you sign up for that service, you should have a token as well as the Pinecone API key. I'm not going to run this. I already put my keys by running this cell. So I'm just going to skip to the next one. So this function is responsible for retrieving the right context based on the query. Here we are passing a limit of how many texts, or what is the window context limitation of our LLM. making sure we don't go beyond that. We are using this vector store query. We want to retrieve the top 3 results, and we want to embed the query using, again, you need to use the same embedding model that was used to populate the index. And then in the process of running this vector store query, we just retrieve the most relevant context and build our prompt. So I run this, so I'm just going to actually run my question with the retrieve. And so this is going to embed the query and get the most relevant information. And then I'm just going to populate the prompt. And this is the exact text that we are passing on to the LLM. And so as you can see here, the way we construct our prompt template in our prompt is to say, answer the question based on the context below. And this is the chunk of data that we retrieve from Pinecone, right? So here, we're mitigating creativity and hallucination from this LLM by saying, only provide an answer based on this context and this information that I'm providing part of the prompt. And so here, I'm just gonna run this cell, and this is gonna invoke the Anyscale endpoint. It's gonna pass the token against the Llama 270B chat model, and we're gonna get the answer. And this is the response, right? So yes, research support streaming. You can look at the experimental gRPC support. And one thing to make sure is that you set the temperature to be very, very low so that it can be as deterministic as possible, or as conservative as possible in providing and generating that answer. Okay, so that includes a demo. One thing I'd like to share quickly is that we have in September, we have a race summit. So if you like what you saw, Vedant is going to be giving a more detailed, in-depth talk about this topic, as well as many and many other industry-leading practitioners. I talk about Instacart, Uber, they're coming back, and many other people are going to be giving the talk and the experiences using Ray, and just LLM and machine learning in general. With that, I'd like to open the floor for questions, and I'm also sharing some relevant link.
Great. Yeah, we'll dive into the Q&A. Now, we have a ton of questions. So we will not be able to get to all of them, but we'll get to as many as possible in roughly 10 minutes. So I'm going to jump right in. What is the maximum size of the documents / sources for RAG pipeline? Can we embed and store infinite numbers of documents in a vector DB and then retrieve the information efficiently?
The answer is yes. Depending on, again, you want to use the correct index for this. So you might not be able to use the starter plan, the free starter plan. But in theory, yes, like there is no upper limit to the number of documents that you can store in a vector database. Great.
How do you select the right similarity metric? For example, when do you use cosine versus Ellucian? And there's been a few questions around similarity metrics. So any additional color we can add to this would be helpful.
Yeah, there's actually a post that I wrote on the Pinecone website about similarity metrics. The differences basically tend to do with the way that the model's loss function was, what loss function was used to train the model. If it's cosine, you would use cosine. If it's Euclidean, you'll use Euclidean. So, like for example, like a lot of image recognition and image like an object limitation models are used to have used Euclidean loss functions to basically train the model. But it's essentially like the concept here is that you want to mirror whatever the model's internal representation is, right? So if it's cosine, you use cosine. If it's Euclidean, you use Euclidean. If it's dot product, you use dot product.
And now regarding the cost for generative, would you recommend using them for internal Q&As for help, support, or rollout for customers, 100K plus customers for unlimited usage?
That's a tough one.
Yeah.
Go ahead, Fee.
Yeah, I was going to say, I don't think there's any perfect answer. I mean, depending on your use cases, you always want to have cost in mind. And so, it's not just the cost of building the application, but the cost of serving LLM, right? So now you can use open source LLM to serve. And so can you first get access to GPU? Can you secondly serve? And what are your business requirements is always something that you want to ask yourself. So, you can start with OpenAI, you can, use AWS Bedrock, or you can use Anyscale endpoint to really, maybe get that application up and running very quickly. And then as you sort of understand how much traffic and you're getting, and, and maybe you have some data privacy concern already in the first place, right? So, depending on how your application is going to evolve, then, I think your option is going to narrow down.
Yeah, I think like what Fee said, just to tag onto that, you would want to do some sort of a proof of concept to get an idea of the cost involved, because it can go, going from like an internal Q&A for, let's say, 100 or 1,000 employees, and then scaling that or providing that to more than 100,000 customers. That's a big, significant lift in cost. So you would want to do some proof of concept within your environment, and then think about the return on investment before you make that decision.
Great, thank you. What's the best way to determine an accurate baseline for semantic search or semantic relevance score? And how do we determine the point of diminishing returns where injecting relevant prompts no longer help?
Do you want to take it? Do either of you want to take this, or do you want me to take that one?
If you want to take a stab at it, and I can add some color.
Okay. I can take a stab at the first part for sure. So the relevance score is determined based on the similarity score, right, between the vector that you queried for and other vectors that exist within your index, right? So it's variable, right? So like if you have a lot of different vectors, your score will vary greatly, right? If you have like 2 vectors in your database, you might have like less variability in the score. So that at least is the first, that answers the first question, right? Like the more vectors that you have, the more variance that you have within those embeddings, right? Like the greater chance that you're going to have of having better similarity scores. But then you also have to kind of decide, and this is subjective, like what would be the cutoff, right, for accuracy that is acceptable to you, right? In some cases, you might only expect to get above 0.9, and in some cases, an answer could have a 0.7 and it still seem relevant enough to be beneficial for your application. So there's like no strict answer to what the exact cutoff should be.
Yeah, Fee, if you don't have anything to say, I'll just say that again, it goes back to having a system that allows you to monitor your application and have a metric that you're using to monitor your RAG application. There are several tools out there. There are several platforms out there that can help you with what we call like LLM ops, and making sure that again, you have a proof of concept. You see the benefits, and then as you start to see that there's a drift, for the lack of a better word, from the results, then you rethink the context that you're providing, or do some sort of think about prompt engineering, or other different ways of improving the output from the application.
Yeah, and I'll just quickly add that, for any application that you plan on, on deploying, you need to have some baseline validation and tests. So similar to the Q&A for LLM, you probably want to have something similar for your semantic search application, and also making sure that you have a human in the loop, or having the opportunity for human to provide feedback on the application and production to flag any odd result or reinforce some of the result, so that you can have that virtual cycle and that feedback loop coming into an application, so that you can improve, or having some kind of feedback, knowing is it good or bad.
How do we deal, or how do we deal with the very, all caps, limited context window or memory of the current LLM models?
Yeah, I think it depends on your use cases. So, the field is moving very quickly. Llama 2 has about 4,000 context window limit. I know already some implementation using ROPE, where it is going to allow you to extend the context window to 32,000, right? So that's definitely one way. But you also have some clever tricks where LangChain has a MapReduce, sort of a way to summarize a smaller chunk of data into a condensed version of the overall data that you can then pass. Again, that's for summarization, is very specific, but I think depending on your use cases, you can get by with a vector database to manage the memory and the context, but sometimes you just need to go with a bigger model.
Great. So when building a semantic search chatbot that always responds in the same language as the language the user speaks it to, and what languages do you need to create your embeddings?
Great question. I think it's more about the alignment and fine-tuning using the instruct technique to really align on how you want the model and the chatbot to speak, the style and the language, and not so much about the context window or the context information that you feed your database.
Anybody else want to add to that? No notes. What are the best practices in terms of chunk size, overlap size, dimension size, and index size? I'm having a lot of success when the index contains lots of documents, but not so much when it's a handful of documents.
Great question.
Go ahead.
So again, it depends on your use cases. You want to try with different chunk of data. There's also different techniques, such as a hierarchy of chunking size. And so based on the question, and if you can programmatically say, well, I need a chunk of different sizes in order to feed the right context, it's all about, are you retrieving the right and relevant context and information to feed a prompt or to feed an LLM. And so imagine you have different strategy, different indices of different chunking data, different sizes. And so, if your use case or your question requires a more broader window of context data, then you may need to query across different chunking sizes, and maybe you can rely on your metadata to sort of filter and get the right query, right? So it's a bit of a lot of fine tuning, a lot of different things to try, not one solution fits all, I would say.
Yeah, I agree with that. I would also say like there's also all these different variables, right? Like, so you don't need so like there's retrieval, and then there's the actual metadata that you're passing to your LLM, right? The actual text or information that you're passing to your LLM. Those don't have to be one and the same. They can be one and the same, right? So you can create chunks, and then those chunks can correspond one-to-one to the vector that represents them. But you can also have chunks that correlate to, say, like a document, right? So like I'm creating small chunks out of a document, and then I'm referencing back the entire document for each one of the chunks, right? And so whatever chunk hits will get that document as a response, right? And you can play around with this, right? Like the fact that they don't have to be correlated one-to-one to get different results and different responses back from your LLM. That's number one. Number two, I think that there was like a mention of like, hey, like this works really well when I have a lot of documents in my index, and not very well when I don't have a lot of documents in the index. And the answer to that doesn't have anything to do with chunking at all, right? That just has to do with the fact that you have more variability in your index and more information to draw on, and so you're going to have better results at the end of the day, right? Like the name of the game with knowledge bases is the bigger they are, the better, right? Because you're going to have a better chance of hitting something relevant to whatever the user is asking you about, right? That's pretty simple.
And to follow up on Roy's point, right? So not a one-to-one, mapping between the retrieval and what you feed into the LLM. And so if you think about it, in the middle, there's a big opportunity for re-ranking or business logic, or, based on the context of the question, reprocessing the information to be more relevant before you feed into the prompt, right? We haven't really talked about, all the different options that you can do, but now that, everything is an interface and API and programming, think of it of re-ranking based on the different sources of data, based on the question, who's asking, and then providing more, or re-ranking or, filtering based on, the retrieval mechanism, right?
And with that, we are at time. So I'm going to say thank you again to our speakers today and remind you guys the recording will be shared with you after the event. And yeah, if you have continuous questions, feel free to reach out to us on the forums, fill out that event survey as well. And we hope to see you at our next event. Round of applause. Woo! Thanks, everybody.
Thanks so much.
Have a good
Thanks,
one.
Vedant. Thanks, Fee. Goodbye.
Okay.